In February of this year, a small group of physicists in Potsdam, Germany, published a single number about the Pacific Ocean: 91.4%. That was their confidence that there would be no El Niño in 2026. None. Not weak, not late, not borderline. Nothing. Now, before you decide what that number is worth, you should know who published it. Since 2012, this group has made 14 forecasts in real time, out loud, in public, before the fact, with their names attached. 13 of them were correct. There is not an operational climate model anywhere on Earth that can show you a scoreboard like that. 4 months later, on the 11th of June, the United States Climate Prediction Center raised an El Niño advisory. Not a watch, an advisory. Conditions were no longer coming, they had arrived. And on the 9th of July, that same agency put the odds of a very strong El Niño by the end of this year at 81%. An event that size would rank among the largest since records began in 1950. 97% that it holds on into next spring. The forecast, with the strongest public track record on Earth, said no. The ocean said yes. Here is what I want you to sit with, because it is bigger than one team getting one call wrong. That gap is a symptom. It is the visible edge of something that has been building for more than a decade, quietly, inside the exact forecasts that decide how your state prepares for hurricane season, what a bushel of corn costs in Iowa, what your utility charges you in January, and whether 20 million people in East Africa receive food before the harvest fails or after. So over the next hour, I am going to show you precisely what broke, when it broke, and why. What it has already cost, in dollars and in lives, from Somalia to Zambia to Peru to Jamaica to the mountains of western North Carolina. Why the National Oceanic and Atmospheric Administration quietly threw out the yardstick it had used to define El Niño since 1950 and replaced it this past February with a completely different one. And the part almost nobody is talking about, the growing evidence that our climate models may be structurally incapable of seeing this coming, because the early warning signal that exists in the real ocean does not exist inside them. One thing before we go into the water. This channel follows stories that live in the data long before they reach the headlines, and this one is still being written. The Pacific is going to keep answering through October, November, and December. When those numbers land, I would much rather bring you the next chapter than start the whole thing over. So subscribe, because the answer is already forming out there on the buoys, and I want us to be ready the moment it surfaces. And do one thing for me in the comments. Tell me where in the world you are watching from, and whether the last El Niño ever actually showed up on your side of the planet, in your rain, your harvest, or your power bill. Now, let's get into it. Right now, as you're watching this, the tropical Pacific is doing something it has done maybe 5 or 6 times in the entire span of reliable measurement. A band of ocean along the equator, thousands of miles from any coastline you have ever stood on, is running hot. In the far eastern stretch of it, the water off the coast of Ecuador and northern Peru is sitting at roughly 2.7 degrees Celsius above its long-term average, which is about 4.9 degrees Fahrenheit. Take a swimming pool and raise it 5 degrees, and you would notice on your skin. Now do it to a corridor of open ocean wider than the continental United States, and keep doing it for months, and you have changed where the world's thunderstorms decide to stand. And that, by the way, is the whole engine, not the temperature, the thunderstorms. Hold on to that because it will matter later in a way you will not expect. In the Central Pacific, the patch forecasters actually watch, a box of ocean about the size of Australia straddling the international dateline. The most recent weekly reading came in near 1.2 degrees Celsius above average, a little over 2 degrees Fahrenheit. That does not sound like much. It is enormous. The equatorial Pacific is the most thermally stubborn place on the planet. Moving it by a degree takes a rearrangement of the entire atmosphere above it. And the atmosphere has in fact rearranged. The index that measures the pressure difference between Darwin, Australia, and Tahiti, the oldest and most stubbornly simple ENSO measurement we have, one that goes back to before radar, before satellites, before computers, has been running at around -25 and -30. In the language of the field, that is coupling. The ocean and the sky have locked arms and started pulling in the same direction. So the forecasters did what forecasters do. They updated. On the 21st of May, the National Oceanic and Atmospheric Administration issued its outlook for the 2026 Atlantic hurricane season and called for a below-normal year. 8 to 14 named storms, 3 to 6 hurricanes, 1 to 3 major hurricanes. 55% odds of a quiet season. The reasoning was almost boilerplate, which is exactly why it is interesting. El Niño develops. El Niño lifts the upper-level winds over the Atlantic. Those winds shear the tops off young storms before they can organize. Fewer hurricanes. Then the ocean kept warming, faster than almost anyone had penciled in. On the 8th of July, the hurricane team at Colorado State University, the group that has been issuing seasonal Atlantic forecasts since the 1980s and effectively invented the format, cut their own numbers again. In April, they had forecast 13 named storms and 2 major hurricanes. By July, they were down to 9 named storms and 1 major hurricane. 1. For an entire season across the Atlantic, the Caribbean, and the Gulf. The physical fingerprints are already there. Wind shear over the Caribbean Sea in early July was running at the second highest level ever recorded for that point in the calendar. The main development region, that long conveyor of warm water stretching from the coast of Africa to the Yucatan, where the big ones are born, has been sitting under a hostile ceiling. As of the middle of July, the Atlantic had produced exactly 1 named storm all year. Tropical Storm Arthur, which came ashore on the Texas coast in mid-June and did not amount to much. If you live on the Gulf Coast, or in Florida, or anywhere along the eastern seaboard, that probably sounds like the best news you have heard in years. And it may well be. But the hurricane season is only the opening invoice. A strong El Niño rewrites the North American winter, and it does it through a delivery system most people have flown through without thinking about it. The subtropical jet stream, that river of fast air about 10 kilometers up, roughly 30,000 feet, the one your pilot rides eastbound to save fuel, gets loaded and dragged south. Storms that would normally track into the Pacific Northwest and Canada get shoved along a southern route instead, across California and the Southwest, over Texas, out through the Gulf states and up the eastern seaboard. The composite picture, built from every El Niño winter since the middle of the last century, looks like this. The southern tier of the United States runs wetter and cooler. The northern tier runs warmer and drier, often by several degrees, and that means the Ohio Valley, the upper Midwest, and New England. Snowpack in the Pacific Northwest suffers. Snowpack in the Southern Rockies often does very well. Natural gas demand in Chicago falls. Reservoir managers in Texas and Oklahoma, sitting on 6 years of drought, start allowing themselves a small amount of optimism. And there is a second, slower effect that shows up in the global thermometer. A large El Niño moves heat out of the ocean and into the atmosphere, and the planetary temperature responds with a lag of roughly 6 months to a year. The first half of 2026 was already the 3rd warmest start to a year in the entire instrumental record, behind only 2024 and 2025. May and June each came in as the 2nd warmest ever measured for those months, as this event took hold. The projections for next year, if this thing peaks where the models say it will peak, are not comfortable reading. So this matters. It matters to your insurance premium, your utility bill, the price of coffee and cocoa and rice, and the water your city drinks. Which is exactly why I want you to notice how confident everyone is. Because we have run this exact experiment before, and it failed. And it failed recently enough that most of you lived through it. Because every agency issuing these outlooks buries the same caveat in the same place, and almost nobody reads it. NOAA's own release says plainly that the seasonal outlook is not a landfall forecast. It says nothing about where or when a storm hits. Colorado State ends every product with a line that has not changed in decades. It only takes one hurricane making landfall to make it an active season for you. Australia's Bureau of Meteorology, watching the same ocean from the other side, put it even more bluntly this year. A strong signal in the Central Pacific does not necessarily mean strong impacts in any particular place, because this pattern is only one of many hands on the wheel. Those are not disclaimers. They are the actual state of the science, printed in small type. Now look at the case that proves it. Rewind to 2023. There was an El Niño that summer and autumn, a strong one. By the traditional measurement, it ranked as the fourth strongest event since 1979. Every seasonal forecaster on the continent knew what that was supposed to mean for the Atlantic. Shear goes up, storm counts go down. The rule had held, more or less, for as long as anyone had been counting. The Atlantic produced 20 named storms that year. The long-term average is 14. Read that again. In the middle of a strong El Niño, the Atlantic ran 40% above normal. The rule did not bend. It broke. And when researchers went back afterward to figure out why, the answer was not that the Pacific had been mismeasured. The Pacific was exactly as warm as everyone said it was. The answer was that the atmosphere had refused to respond. That the thunderstorms, the actual mechanism by which the Pacific reaches across 10,000 miles and touches a hurricane over Barbados, never fully lit up where they were supposed to. The ocean sent the signal. The sky did not carry it. So the question hanging over this hurricane season, and over the winter after it, and over the corn crop, and the reservoirs, and the gas bill after that, is not really, how strong will this El Niño be? It is, will it behave like an El Niño at all? Nobody in this field will tell you the answer with a straight face right now. And to understand why they can't, why the most heavily instrumented, most intensely studied climate pattern in the history of science has become a coin flip in the hands of people with supercomputers, we have to go back to a night in the autumn of 1982, when the largest El Niño of its century was already tearing the Pacific apart, and not one forecaster on Earth could see it. Not because they weren't looking, because a volcano had painted the sky. On the 28th of March, 1982, a mountain in the state of Chiapas in southern Mexico came apart. El Chichon had not erupted in 500 years. Almost nobody had it on a watch list. Over about a week, it threw one of the largest sulfur plumes of the 20th century into the stratosphere, and by that summer, the resulting haze had spread across the northern tropics and beyond. Sulfuric acid droplets in the stratosphere do something specific, and in this case, catastrophic. They interfere with the infrared radiation that satellites use to read the temperature of the sea surface. The instruments were working perfectly. The physics of the retrieval was sound, but between the ocean and the sensor, there was now a veil, and the veil made the water look colder than it was, in places by as much as 2.5 degrees Celsius, roughly 4.5 degrees Fahrenheit, and it stayed that way for months. So here is the picture. In the summer and autumn of 1982, the equatorial Pacific was heating up toward what would become, at that time, the strongest El Niño ever measured. And the primary global monitoring system was reporting that the ocean was cool. The rest of the observing network was almost nothing. A scattering of temperature readings taken by merchant ships as they crossed the basin, a handful of tide gauges, a few current meters on the equator, and critically, almost none of it transmitted in real time. The data came back on tapes and in logbooks, weeks or months later, to be analyzed by people who by then were reading history rather than watching weather. In September of 1982, a research vessel in the Eastern Pacific finally put instruments in the water and found sea surface temperatures about 5 degrees Celsius above normal. 9 degrees Fahrenheit. The layer of warm water at the surface was roughly 4 times thicker than it should have been. The cold undercurrent that normally runs east along the equator had simply stopped. The marine life that ordinarily swarms those waters was gone. By the time the world understood what was happening, it had already happened. What followed is the reason this story matters beyond a graph. Record rainfall and catastrophic flooding in Ecuador and northern Peru. The city of Guayaquil took more than 13 times its normal rain. Drought across Australia, Indonesia, and New Guinea. A rare hurricane striking Hawaii. 6 major cyclones through French Polynesia. On Christmas Island in the Central Pacific, roughly 17 million seabirds abandoned the colony, leaving their chicks behind, because the fish beneath them had vanished. In California, a winter of relentless storms tore up the coastline. Off the west coast, upwelling collapsed, and the fisheries went strange for 2 years. And there was a bill. 2 researchers at Dartmouth published a study in 2023 in the journal Science that did something the field had never properly done. It followed the money forward. Not the damage during the event, the depressed economic growth in the years afterward, country by country, as harvests failed and infrastructure went unrepaired, and the effects compounded. Their accounting put the global income lost to the 1982 and 83 El Niño at $4.1 trillion. For the 1997 and 98 event, $5.7 trillion. Those numbers are almost too large to feel. So here is a way to hold one of them. $4.1 trillion is on the order of what the entire United States federal government spent in a year in the middle of the last decade. From one warm patch of ocean that nobody saw coming. The scientific community's reaction to 1982 was, I think, one of the more admirable things any field has ever done. They did not argue about whose fault it was. They built an eye. The program was called the Tropical Ocean and Global Atmosphere Project, and it ran from 1985 to 1994, pulling in the United States, Japan, France, and others. Its physical legacy is a line of moored buoys strung across the equatorial Pacific, about 70 of them at full strength, from the coast of South America almost to Indonesia. Each one is anchored to the seafloor in water that can be 3 or 4 miles deep, 5 or 6 kilometers. Each one measures the wind, the humidity, the air temperature, the sea surface, and then reaches down through the water column and takes temperature at 10 separate depths, down to about 500 meters, roughly 1,600 feet. 5 of them, sitting directly on the equator, measure the speed of the current itself, and every reading goes up to a satellite and down to a lab within hours. Think about what that changed. Before, we were a doctor listening to a patient's chest from across the room. After, we had a line of sensors inside the artery. Japan built its own version for the Western Pacific, and by the middle of the 1990s, the line was essentially complete. A dedicated NOAA research vessel came into service in 1996 to maintain it, and the following year, Congress put the whole array on long-term funding. I want to be honest about what that line actually is, though, because the romance of it will matter far less than the maintenance. A moored buoy in the open equatorial Pacific is a hard object living a hard life. Salt eats it. Sun cracks it. Barnacles colonize the sensors. Fishing vessels tie up to it because a buoy attracts fish. And sometimes gear gets tangled, and lines part, and instruments go over the side. Occasionally, a mooring is simply stripped. Every one of those buoys has to be physically visited by a ship, a real ship, with a crew, burning fuel, weeks from any port, and swapped out on a rotation. Take away the ship, and the array does not fail dramatically. It fades. Sensor by sensor, gap by gap, the picture goes grainy. And it does it slowly enough that nobody has to hold a press conference. Remember that. It becomes the most important sentence in this entire story. For now, though, the timing could not have been better if it had been scripted. Because in early 1997, the buoys started reporting something. Deep in the Western Pacific, hundreds of feet below a surface that still looked ordinary, a mass of warm water was on the move, heading east. The surface had not told the story yet. The subsurface had. For the first time in human history, a major El Niño was called months before it arrived. And then it delivered, more or less on schedule. That winter, California took a beating from a conveyor belt of storms, flooding, mudslides, coastal erosion, a state of emergency across dozens of counties. The northern tier of the country had one of its mildest winters in memory, and on a single night in late February of 1998, a tornado outbreak tore across central Florida in the dark and killed more than 40 people, in a state that does not think of itself as tornado country, during a season the shifted jet stream had made unusually violent. None of that was prevented by the forecast. Weather cannot be prevented. But agencies pre-positioned equipment, utilities hedged. California cleared storm drains and reinforced levees before the water came, instead of during. Fisheries managers off Peru cut anchovy quotas ahead of the collapse, rather than after it. Water districts, insurers, and grain traders all got something they had never had before in the history of the human species. Several months of warning that the global climate was about to change shape. Not certainty, and not precision either. What they got was lead time, which, if you have ever watched a hurricane cone narrow over your own county, you already know is the most valuable substance in this entire field. Now, none of that would have made sense without two men who never met the buoys and never saw a satellite image. The first was Gilbert Walker, a British physicist working in colonial India in the early 20th century, running a monsoon forecasting office and drowning in numbers. Sifting through decades of pressure readings, he found a strange, slow rhythm. When barometric pressure was high over the eastern Pacific, it was low over Indonesia and northern Australia, and vice versa. And the whole thing rocked back and forth on a cycle of a few years. He called it the Southern Oscillation. He did not know what caused it. He did not connect it to the ocean at all. Picture a seesaw laid across the tropical Pacific. One end sits over Indonesia, the other over the coast of South America. Air pressure rises on one side as it falls on the other, and the trade winds are simply what runs down the tilt. Hold that image. We are going to come back to it, and by the end of this story, it is going to mean something very different than it does right now. The second man was a Norwegian meteorologist working in California in the late 1960s. He looked at the pressure seesaw and at the temperature of the ocean underneath it, and said something that now sounds obvious and was then radical. These are not two phenomena. They are one. The sky is not sitting on top of the ocean. They are wired together, each one feeding the other, and the whole coupled thing is what we should be studying. That insight is the reason the word ENSO exists. The El Niño Southern Oscillation, the ocean half and the atmosphere half welded into one name. That idea, wired into a line of instruments, is what produced the triumph of 1997, which makes what happened to those buoys between 2012 and 2014 genuinely difficult to explain to anyone outside the field. Because the data flowing back from that line collapsed to a record low of 30%. That was the eye we built after being blinded. And outside a handful of laboratories, almost nobody noticed.
The collapse has a cause, and the cause is smaller and more ordinary than anyone would like. First, you need to understand what those boys are actually listening for, because it is not temperature. Temperature is the symptom. The thing they are listening for is a loop. Here is the engine, and I promise to be quick about it, because the mechanism matters far less than what happens when it stops behaving. Under normal conditions, the trade winds blow from east to west along the equator. They have been doing it since long before there was anyone to notice. As they blow, they drag the surface water with them, piling warm water up against Indonesia and the Philippines until the sea there actually stands higher than it does off Peru, by around half a meter, roughly 1.5 feet, which is an absurd thing for an ocean to do. That pile of warm water is called the warm pool, and it is the biggest concentration of ocean heat on the planet. Above it, air rises. Rising air makes towering thunderstorms. Those thunderstorms pull more air in beneath them, which strengthens the trade winds, which pile up more warm water, which builds more thunderstorms. You have already heard what that is. Hold a microphone up to its own speaker. The system starts listening to itself, and a whisper becomes a scream. Not because anyone turned up the volume, but because the output has become the input. Now weaken those winds, just slightly, just for a few weeks. The pile of warm water sags eastward. Thunderstorms follow the warm water into the central Pacific. The trades weaken further because the storms that fed them have wandered off. The warm water slides further east. The loop is now running in reverse, and it will amplify itself just as eagerly in this direction as it did in the other. That is El Niño, a feedback loop that has flipped its sign, dressed up as a warm patch of water. Beneath all of it, there is a second layer to the story, and it is the layer the buoys care most about. Between the warm surface water and the cold abyss, there is a boundary, a temperature cliff called the thermocline, sometimes only a few tens of meters thick, where the water goes from bath water to near freezing over a shockingly short vertical distance. Picture a bathtub you are slowly tilting. Warm water sloshes toward one end. The thermocline is the slanted line between the warm layer on top and the cold below it. When the trades pile warmth in the west, that boundary tilts down deep in the west and rides shallow in the east, close enough to the surface that the wind can pull cold water up into the sunlight along the South American coast. That upwelling is why the Eastern Pacific is one of the most productive fisheries on Earth. Stop tilting the tub, and the water sloshes back. The thermocline levels out. In the east it sinks. The cold water can no longer reach the surface, and the sea off Peru warms, not because the sun got stronger, but because the cold stopped arriving. This is the part that gives forecasters their lead time. Before a big El Niño, heat accumulates in the upper layers of the Western Pacific like charge building in a battery. Measure that heat, and you know the system is loaded. That is exactly what the boys saw in early 1997. But loaded is not fired. The trigger is something almost embarrassingly small. A burst of westerly wind in the Western Pacific lasting a week or two. Sometimes it comes out of a pair of tropical cyclones straddling the equator. Sometimes it comes out of a slow-moving pulse of tropical thunderstorms that circles the globe every month or two.
These bursts shove the warm pool eastward and launch a slow, invisible bulge of warm water beneath the surface, a wave that takes 2 or 3 months to cross the Pacific, and that nobody standing on a ship would ever see. Warm water loaded in the west, a wind burst to release it. That is the recipe. But before we go to the barrier, I owe you the last link in the chain, the one that turns a warm patch of water near the dateline into a flooded street in Sacramento or a green Christmas in Minneapolis. Because the ocean itself does absolutely nothing to you. The ocean cannot reach North America. The atmosphere does the reaching. Here is how. When the warm water shifts east, the towering thunderstorms shift east with it. And those storms are not just weather. Each one is a chimney, pumping enormous quantities of heat from the sea surface up to the top of the troposphere, 10 miles above the water.
Do that continuously, over an area of ocean the size of a continent, and you have installed a heat source in the upper atmosphere, in a place where the atmosphere is not used to having one. The upper atmosphere responds the way a fluid always responds to a lump. It makes a wave. That wave propagates north and east out of the tropics in a chain of alternating high and low pressure centers, arcing over the North Pacific, dropping across North America. It bends the jet stream. And the jet stream is the conveyor that decides where every storm in the country goes for the next 3 months. So the sequence is, warm water moves, thunderstorms follow, thunderstorms punch heat upward, the upper atmosphere buckles, the jet stream bends, and your winter changes. Which means the thunderstorms are the transmitter, and the water is only the reason the transmitter moved. Burn that into memory, because everything that has gone wrong in the last 5 years lives in the gap between those two things. Between an ocean that warms exactly as predicted and an atmosphere that declines to broadcast. And in the spring, when forecasters most need to know what the rest of the year holds, every ingredient in that chain is almost impossible to read. This is the spring predictability barrier, and almost everything that follows runs through it. In March, April, and May, the feedback loop I described is at its weakest point in the annual cycle. The signal in the ocean is small. The random noise from the atmosphere is at its loudest relative to that signal. The wind bursts, the passing storms, the general chaos. And critically, this is the moment when events are born or aborted. So the exact season when a decision is being made is the season when the system is least readable. Try to call the side of a coin while it is still spinning on its edge. A second later it will be obvious. Right now it is not, and no amount of computing power will fix that, because the answer does not exist yet. Every forecaster in the world knows about this barrier. It has been described in the literature since the 1990s. So the honest question is not whether it exists, it is how bad it actually is, in practice, in the real forecasts that governments and grain traders and insurance companies use. In 2024, a team including researchers at Columbia University and the Climate Prediction Center published exactly that audit in the journal NPJ Climate and Atmospheric Science. They took every real-time model forecast issued over 22 years, from 2002 through 2023, dozens of models, both the physics-based ones and the statistical ones, and asked a simple, brutal question. How often did they correctly call the onset of an event? Beyond the first 3 forecast seasons, accuracy fell below 20%. And here is the part that should stop you cold. None of that is a hindcast, and none of it is a laboratory exercise where you already know the answer. That is how the operational forecasts that real institutions budget against actually performed. In real time, over 2 decades,
in the era of the buoys and the satellites and the supercomputers. Below 20%. Now, that number is not the scandal it sounds like at first. Forecasters have always been upfront about the spring barrier, and a forecast made at short lead is a very different animal from one made at long lead. The models do have real skill inside about 6 months. Nobody is claiming otherwise. But keep that number in your pocket, because in a moment, we are going to watch what happens when everyone forgets it. In the spring of 2014, every box on the checklist I just walked you through was ticked.
The warm water was stacked in the west, in quantities that looked like 1997 all over again.
The westerly wind bursts came, one after another. The models agreed almost unanimously. And then, in July, something reached across from the Indian Ocean and switched the whole thing off. If you were paying any attention to weather news in the first half of 2014, you remember the drumbeat. A monster was coming. The warm water volume in the equatorial Pacific rose through the winter and into the spring at a rate that had one obvious historical analog. Strong westerly wind bursts hit the western Pacific in January, in February, in March. A powerful subsurface wave of warmth started east. Newspapers ran the phrase, Super El Niño. In California, then in the third year of a drought severe enough that towns were trucking in water, and the governor had declared a state of emergency, the coverage took on something close to hope.
An El Niño was going to come and break it. And then, in July, the trade winds did something nobody had asked them to do.
Instead of relaxing further, they surged. A strong pulse of easterly wind swept the equatorial Pacific, pushing the warm water back to the west, shoving the whole system back downhill. The event stalled. By December, the tropical Pacific was hovering at the borderline, technically warm, atmospherically inert. The monster never showed up. Now, a stalled forecast is not automatically a scandal. The spring barrier is exactly the kind of thing that produces this outcome, and it had produced it before, in 1990. What made 2014 different was the confidence. The models had not offered a possibility. They had converged. So people went looking for the culprit. And what they found is, in my view, the hinge on which this entire story turns.
One line of investigation, published in scientific reports by 2 oceanographers, including a physical oceanographer at NOAA's Pacific Marine Environmental Laboratory in Seattle, pointed somewhere the textbooks had not been looking: the Indian Ocean. The Indian Ocean that year was running unusually warm, and the warm Indian Ocean, it turns out, changes the pressure pattern over the western Pacific in a way that weakens the very westerly wind anomalies El Niño needs to keep growing. The signal was not just Pacific anymore. Another ocean, 6,000 miles away, nearly 10,000 kilometers, had a hand on the switch. Sit with the implication. The mechanism I described to you, warm pool, thermocline, wind burst, feedback, is a Pacific mechanism. It is a closed system. It is what our forecasting models were built to simulate, and it is beautiful, and it works. And 2014 was the field's clearest evidence yet that the closed system is not closed. That there are other conductors in the orchestra, and they do not always follow the Pacific's tempo.
A second twist explains why 2014 is remembered at all. The Seattle oceanographer and a colleague published a follow-up finding. Those same easterly winds that killed the event also prevented the ocean from discharging its heat. Normally, an El Niño is how the tropical Pacific dumps accumulated warmth into the atmosphere and toward the poles. It fires, it empties, and it takes years to reload. That year, the trigger never pulled. The heat stayed in the magazine. Under ordinary conditions, they estimated, the odds of any El Niño forming in 2015 would have been somewhere around 27%. With that trapped reservoir sitting under the Western Pacific, the odds rose to roughly 40%. And in 2015, a sustained run of westerly wind bursts arrived, hit that loaded reservoir, and produced one of the 3 strongest El Niño events ever recorded. So the failure of 2014 created the giant of 2015. The miss was not noise. The miss was the setup. Which brings us back to California, and to a lesson that almost nobody drew at the time. Through the autumn of 2015, the coverage went from hopeful to nearly triumphant. Here was a top 3 El Niño arriving on schedule, aimed at a state that had spent 4 years watching its reservoirs turn into cracked mud and its wells run dry. The composites all said the same thing. Strong event, southern storm track, wet winter in Southern California. Homeowners cleaned gutters, counties handed out sandbags, reporters flew to Los Angeles to stand in front of empty flood channels and explain what was about to fill them. Southern California finished that winter still in drought. Northern California did considerably better. The Sierra snowpack recovered somewhat, and the statewide emergency stayed in place for another full year before it was finally lifted in the spring of 2017. The event was real. The event was huge. The event did roughly what the ocean said it would, and the rain, for millions of people who had been told to expect it, did not arrive where the map promised. Blaming a single forecast for that misses the point. The warning is about the tool. A composite map, the kind you see in every news segment with red here and blue there, is an average of a small number of past events. Since 1950, there have been only a couple of dozen El Niño winters, and no 2 of them put the warm water in exactly the same place, or coupled with the atmosphere in exactly the same way, or arrived on top of the same background state. Averaging them produces something that looks like knowledge and behaves like a suggestion.
We have been handing the public an average and calling it a forecast. And for a long time that was good enough, because the events themselves stayed close enough to the average that the trick worked. They have stopped staying close. There is one more finding from that period that I want to put in front of you, because it is the most uncomfortable one, and it comes from inside the house. A team including forecasters at the Climate Prediction Center and a statistician at Columbia went through nearly 4 decades of forecasts from the American Multi-Model Ensemble, the collection of physics-based models that underpins the official United States outlooks. They were looking for a systematic flaw, and they found one. Forecasts launched in April, May, and June carry what they called excessive momentum. Put simply, when the models are started after a stretch of warming, they predict more warming. When they are started after cooling, they predict more cooling. They lean too hard on the direction of travel, and not hard enough on the possibility of a turn. In some of the models, this appeared to come from the model's own formulation, not from bad starting data, but from how the thing was built. A car with a steering wheel that sticks slightly in its last position. On a straight road, you would never know. On a curve, it decides everything. And 2014 was a curve. The field absorbed all of this, wrote it up, filed it, and largely treated the year as a freak, an unlucky collision of a stubborn Indian Ocean and an unhelpful burst of easterly wind. A one-off. Then the one-offs started arriving in a row. The first of them refused to leave for 3 years. It broke the theory of how these events are supposed to end, and while it sat there, unmoving, over the coldest water the Eastern Pacific had produced in a generation, 5 consecutive rainy seasons failed across the Horn of Africa, something that had never once happened in 70 years of records, and something the world's most advanced climate models had projected would not happen at all. Let's take those in order. First, the ocean, then the people. La Niña is the same engine running the other direction.
The trade winds strengthen instead of slackening. The warm pool packs harder against Indonesia. Cold water comes up along the eastern equator with more force than usual. The sea off Peru chills, and the whole planetary circulation leans the opposite way from everything I just described. Where El Niño floods northern Peru, La Niña parches it. Where El Niño puts a lid on the Atlantic hurricane season, La Niña takes the lid off. Something about La Niña makes the last 5 years very difficult to explain. La Niña is supposed to be an ending.
In the standard picture, the one in every textbook, the one our forecasting models are built around, a large El Niño empties the tropical Pacific. It takes the heat that has been stacking up in the west for years, and it spends all of it, dumping it into the atmosphere and shunting it toward the poles. When it is over, the basin is left in deficit, cold, discharged. And La Niña is what that deficit looks like from the outside. The system overshooting on its way back toward the middle before it slowly reloads. 2 to 7 years. 2 to 7 years is the rhythm we teach in every introductory class on Earth's climate. In 2020, La Niña arrived without an invitation. There had been no big El Niño before it, no discharge, no deficit worth speaking of. The Pacific went cold from a starting condition that, according to the theory, should not have been able to produce a La Niña at all. And then it stayed cold. Through 2021, through 2022, into the early months of 2023. 3 consecutive years. Forecasters call it a triple dip, and it is rare enough that in the entire span of reliable instrumental record, there are only 3 of them. The mid-1970s, the turn of the millennium, and this one. And the other 2 behaved themselves. Both followed a strong El Niño. Both fit the theory. Both were, in the technical sense, boring. This one arrived out of the wrong initial state, sat there for 36 months, and would not be reasoned with. So the field went looking for a mechanism, and what came back was not one answer. It was 4, from 4 different directions, and none of them lives inside the tropical Pacific. One group found unprecedented cross-equatorial winds blowing up from the southeastern tropical Pacific, a southerly push that had no precedent in the record, and that kept the cold tongue fed. Another group ran a 100-member ensemble of a Japanese climate model and concluded that the second year of the event was driven from the North Pacific atmosphere, thousands of miles from the equator, rather than from anything happening in the tropics. A third pointed at the Indian Ocean, where a strong dipole event in 2019 may have lit the fuse, and at the Atlantic, where a warm anomaly off Africa may have helped keep the trade winds cranked. And a fourth line of work proposed that warm water was being physically ferried through the Indonesian archipelago into the eastern Indian Ocean, and then propagating back east as subsurface waves, extending the whole thing by holding heat in the western Pacific longer than it should have stayed. There is even a hypothesis, and I want to be very clear that it is a hypothesis, disputed and not settled, that the smoke from the Australian bushfires of 2019 and 2020 brightened clouds over the southeast Pacific enough to nudge the system into its cold phase. Take a step back from the details and look at the shape of that list. Every single explanation on it involves something outside the Pacific Basin, or outside the tropics entirely. Every single one describes a system with more hands on it than the theory allows. The Seattle oceanographer who has spent his career on these events put it about as plainly as anyone has. Compared with a single-year event, a 3-year cold phase raises the risk of drought, flood, and heat disaster for the simple reason that it lasts long enough for coping strategies to fail. Which brings us to the people. Rainfall in the eastern Horn of Africa, Somalia, eastern Ethiopia, northern Kenya, comes in 2 seasons. There is a long rain season in March, April, and May, and a short rain season in October, November, and December. Everything depends on them. The pasture, the boreholes, the maize, the sorghum, the camels and goats and cattle that are not livestock in the American sense, but a family's entire savings account, walking around on 4 legs. Beginning in late 2020, those seasons started failing. Not 1, not 2, 5 in a row. That had never happened before in 70 years of reliable rainfall data. In the Shabelle and Juba river basins, rainfall totals fell to the lowest levels recorded since 1981. The Santa Barbara drought researcher who runs the analysis behind the American Famine Early Warning System described one of those seasons in terms that stay with you. Something on the order of 5 inches of rain, about 13 centimeters, spread across 3 months in a place that hot is, functionally, no rain at all. The soil takes it, and the sun takes it back before a root ever gets a share. Now think about what a failed season actually means to a household, because the number is not the story. 1 bad season, you sell an animal. It hurts, but you eat. 2 bad seasons, you sell more animals into a market where everyone else is also selling, so the price collapses just as you need it most, and you start borrowing. 3, the borrowing is gone and the herd is thin, and you are walking further every day for water. 4, the breeding females start dying, which means the herd cannot recover even if the rain comes tomorrow. 5, you are on a road somewhere with your children and whatever you could carry. By the end of it, roughly 1,400,000 Somalis had been displaced. 3,800,000 livestock were dead. More than 20 million people across the region needed food assistance. The formal technical threshold for declaring famine was, in the end, not crossed. An outcome that belongs squarely to an enormous humanitarian effort. But people died anyway, of hunger and malnutrition tangled up with disease outbreaks in numbers that nobody will ever count precisely. And then, in the spring of 2023, it flipped. Rain came early and came hard, and an astronaut aboard the International Space Station photographed the Shabelle River overtopping its banks near the Ethiopian border, brown water spreading out across land that had been dust for 3 years. Drought did not end. It was simply joined by flooding, on ground too baked to absorb anything. And East Africa was not the only place paying. The same 3-year cold phase was reshaping weather on 4 continents simultaneously. Australia took the mirror image of the Horn's drought. Back-to-back years of extraordinary rainfall and flooding down the eastern seaboard. Entire towns in New South Wales and Queensland going under twice within months. Insurance losses that broke national records. And across the American Southwest, the same stretch of years produced the deepest point of a drought that tree rings suggest is the driest multi-decade period the region has seen in 12 centuries. If you live in Phoenix, Las Vegas, Denver, or Los Angeles, you watched the consequence on the evening news without necessarily connecting it to the Pacific. Lake Mead dropped to levels not seen since it was first filled in the 1930s, exposing intake towers, sunken boats, and eventually human remains. The federal government declared the first ever shortage on the Colorado River. 7 states spent 2 years in negotiations over water that existed on paper and did not exist in the reservoir. No single one of those events was caused by La Niña. Climate does not work that way, and anyone who tells you a drought has one cause is selling something. But the odds were tilted, and they stayed tilted, for 3 consecutive years, in the same direction, across a hemisphere. That is what the Seattle oceanographer meant about duration. A single bad season is weather. 36 months of loaded dice is a different kind of event entirely, one that outlasts emergency budgets, aid appeals, reservoir buffers, and the patience of the people living inside it.
Now here is the detail that has nothing to do with rainfall, and everything to do with why you are watching this. For years, the major global climate models had projected that this exact region would get wetter. More spring rain, not less. Meanwhile, the observations, going back to the mid-1980s, showed the long rains drying out. Researchers had a polite name for the contradiction.
They called it the East African climate paradox, which is what a field calls a problem when it does not yet have a solution. The models had the direction of travel backwards, which is a deeper kind of wrong than getting the amount wrong. And what did work? Tailored forecasts, built not from the full physics of a global climate model, but from the observed temperature of the ocean surface, meaning the gradient across the Pacific and the state of the Indian Ocean, mapped statistically onto East African rainfall. The Famine Early Warning Network was calling these poor seasons months ahead. They said, in advance and in public, that the October to December season of 2021 looked like the disastrous season of 2010, and that the spring of 2022 looked like the spring of 2011. They were right both times. So we had a situation where the simpler tool, watching the ocean directly, beat the more sophisticated tool that was supposed to simulate it. No one who works in climate modeling enjoys that sentence, and I do not say it to score a point. Those models are among the most impressive artifacts human beings have ever built. But that failure over East Africa was not a regional quirk, and it was not bad luck. It traces back to a single temperature trend in the tropical Pacific, a trend that has been running for more than 40 years, a trend that every satellite, every ship, and every buoy in the water agrees on completely, and a trend that essentially no state-of-the-art climate model on Earth can reproduce. Once you see it, you cannot unsee why the seasonal forecasts drift the way they do. Here is the observation, and it is so simple that it takes a moment to appreciate how strange it is. Since about 1980, the global ocean has warmed. All of it, essentially. You can pick almost any patch of sea surface on the planet, and the trend line runs uphill, except for one place. The eastern equatorial Pacific, the cold tongue that stretches west from the coast of South America, has been warming far more slowly than the rest. In some subregions, over some stretches of that record, it has actively cooled. At the same time, the western Pacific warm pool has warmed briskly. So the temperature difference between the two ends of the basin has been getting stronger, not weaker. That west to east gradient is the thing that drives the entire system, and the atmospheric circulation that sits on top of it, the great overturning cell that runs west along the surface and east up high, has strengthened right along with it. The trade winds have picked up. Go back to that seesaw for a second. For 40 years, one end of it has been tilting further down and the other further up. The whole apparatus has been leaning harder into its own bias. Now here is the problem. When you run the major climate models, the same generation of models that inform national assessments, that feed the seasonal outlooks, that underpin the projections governments plan around, they predict the exact opposite. In the model world, greenhouse warming heats the eastern Pacific faster than the west, the temperature gradient weakens, and the overturning circulation slows down. That has been the expected outcome for decades, and it is physically reasonable. A warmer atmosphere holds more moisture, the tropical circulation has to slow to stay in balance, and the cold tongue, which is thin and easily disturbed, should be the first thing to give. The ocean has spent 40 years doing the reverse. And this is not a matter of degree, or a signal buried in noise that reasonable people could argue about. One analysis found that the observed change in the pressure gradient across the Pacific lies outside the range of natural variability produced by every model they examined. Not most of them. All of them. When your observation sits outside the entire spread of your model ensemble, you no longer have a slightly imperfect model. You have a missing process. So where is it missing? There are three serious candidates,
and I want to walk you through them, because the disagreement is the interesting part. The first is called the Ocean Dynamical Thermostat, and it goes back to work done in the 1990s. The idea is that the cold tongue is not really made of surface water at all. It is made of water that sank in the North Pacific and the Southern Ocean decades or centuries ago, traveled along the bottom, and is now being dragged back up along the equator. That water has not been in contact with our atmosphere. It has not felt any of the warming we have added.
So as the surface of the world heats up, the equator keeps pulling up cold, old water that does not know about it, and the temperature gap widens, which strengthens the winds, which pulls up even more of it. The tap in your kitchen runs hot the moment you turn it, because the pipe is short. The equatorial Pacific is a pipe that is a century long. The second candidate says the fault is not in the tropics at all. A team using what are called pacemaker experiments, where you force a model's ocean outside the tropics to follow the real observed temperatures, and then let the tropics do whatever they want, found that they could reproduce the observed strengthening of the circulation almost exactly, which points the finger somewhere unglamorous. The subtropical and extratropical South Pacific, off the coast of Chile and out toward Antarctica, a region the models handle poorly, and where almost nobody was looking. The third is about clouds, and specifically about the deck of low, flat marine cloud that sits over the cool water off South America, the same kind of overcast that gives coastal California its gray mornings. Cooler water makes more of that cloud. More cloud reflects more sunlight, which cools the water further, which makes more cloud. It is another self-reinforcing loop, and one analysis found that models with too weak a version of it systematically underestimate how much multi-decade cooling the Eastern Pacific can generate on its own. A fourth strand of work, published last year, argues that the models do produce some cooling at depth in response to the historical forcing. They simply fail to deliver it to the surface because their wind-driven circulation and their vertical mixing are not moving it upward the way the real ocean does. Notice something about all four. They are not really competing theories about El Niño. They are four different accounts of how the models are misplumbed, and the honest position, held by most of the people who work on this, is that we do not yet know how much of the observed 40-year trend is a forced response to greenhouse gases, and how much is slow internal variability that will eventually swing back. That uncertainty is real, and I am not going to paper over it. But I want you to see how far the consequences travel, because this is not a niche argument about one stretch of equatorial water. The tropical Pacific is the metronome for a very large fraction of the world's rainfall. Whether that west to east temperature gap widens or narrows over the coming decades determines whether the American Southwest dries further or recovers. It determines whether the East African long rains stabilize or keep failing. It shapes the monsoon over India, the dry season in the Amazon, the fire weather in Indonesia and Australia. Every long-range water plan on Earth, every reservoir a city is deciding whether to build, every aquifer a state is deciding whether to drain, is resting, somewhere in the fine print, on a projection of what that gap is going to do. And the models projecting it have spent 40 years getting the sign of the recent trend backwards. Which is exactly the kind of sentence that gets clipped and posted without the rest of the paragraph, so let me be precise about what it does and does not mean. It does not mean the models are wrong about global warming. The global temperature projections have held up remarkably well, decade after decade. That part of the science is not in doubt, and this is not that argument. What it means is narrower and, in its own way, more interesting. In one specific region, on one specific pattern, the models and the ocean have been telling different stories since before most of you were born, and nobody has yet closed the gap. But whichever way it resolves, there is an operational consequence that is not uncertain at all.
And it is the reason I have taken you through all of this. If your model warms the Eastern Pacific too fast in its century-scale trend, it is also warming the Eastern Pacific too fast in its 6-month forecast. The bias does not politely confine itself to the long timescales. It leaks. The lead forecaster at the Climate Prediction Center, working with a statistician at Columbia, published exactly that finding in 2022. The American Multi-Model Ensemble, the collection of physics-based models behind the official United States outlooks, produces temperature trends in the central and eastern equatorial Pacific that are more positive than the trends actually observed between 1982 and 2020. And their conclusion, stated carefully in the way these things get stated, is that trend errors of this kind should be expected to increase the number of El Niño false alarms. Think about what that means in practice. Not a random error, which averages out over many forecasts. A systematic lean. Every spring, the models put their thumb very gently on one side of the scale. A clock that gains a minute a day is perfectly adequate for catching a train this afternoon. Run it for 6 months without checking, and you will show up on the wrong day. 3 years later, a follow-up study made it worse and more specific. A researcher at the University of Washington, working with that same forecaster and a colleague, went back through the high-confidence spring forecasts, the ones where more than 3/4 of the ensemble members agree, the ones a forecaster would feel comfortable leaning on, and found that they are systematically overconfident. When those confident calls fail, they tend to fail in the same way. The models hold their equatorial temperature anomalies too long. Their rainfall response along the edge of the warm pool is too deterministic, too eager to fire. And they lean too heavily on tropical Pacific signals while underweighting what is happening in the subtropical Northeast Pacific, which is, of course, exactly the kind of outside-the-basin influence that showed up in 2014 and again in the triple dip. So now hold two facts side by side. The models drift warm in the tropical Pacific, and the real ocean, globally, is warming everywhere. Which means the yardstick we have used to define these events since 1950, a fixed temperature departure in one box of ocean, measured against a 30-year average, has been quietly measuring the wrong thing for years. If the whole tropical belt rises by 1/3 of a degree, then a Pacific that is merely keeping pace with the rest of the world will register as a warm event. It will trip the threshold. It will get a name, and a press release, and a set of composite maps. And the atmosphere, which does not care about our thresholds and only responds to differences, will do nothing at all. On the 1st of February this year, the United States stopped using that yardstick. The change was announced in a public information statement from the National Weather Service headquarters, dated the 13th of January, 2026. It is 2 pages of the driest prose you will ever read. It is also, I would argue, one of the more significant things to happen in operational climate science this decade. Here is what changed. The traditional index takes the sea surface temperature in the Niño 3.4 region, the box straddling the dateline, and subtracts a 30-year average. Simple. Stable. Wrong, increasingly, for the reason I just gave you. The new index takes the same regional temperature and subtracts something else, the average temperature anomaly of the entire tropical belt, from 20 degrees south to 20 degrees north. Everything from Rio to Riyadh to Jakarta, all the way around the planet. Then it rescales the result so the numbers still feel familiar to forecasters who have been reading the old ones for 30 years. In plain terms, instead of asking how warm the Pacific is, we now ask how warm the Pacific is compared to the rest of the tropics. If you want the everyday version, it is inflation. Imagine judging whether a house is expensive by quoting its price in $1950 and never adjusting. Every year, more houses look expensive, not because anything about them changed, but because the currency did. That is precisely what has been happening to El Niño. We kept quoting the ocean in $1950. And now, the seesaw. All those decades, we were measuring how high one end of it sat above the ground. It worked beautifully, right up until the ground itself started rising. The new index measures the tilt. Australia got there first, which I think deserves mentioning. Their Bureau of Meteorology switched to relative indices in September of 2025, 5 months ahead of the Americans. New Zealand followed. India has been weighing it. This is one of those rare cases where a quiet, technical decision propagated through half the world's weather services in under a year, because everyone was looking at the same problem, and nobody wanted to be the last one holding the old ruler. So what actually changes when you swap them? 2 things, mostly. El Niño events generally look weaker under the new index. La Niña events generally look stronger, and the entire historical record has been recalculated, going back to 1950, so that an event from the middle of the last century and an event from last year can be compared on equal terms, which, until this year, they could not be. Some of the reclassifications are striking. Take September of 2024. By the traditional measurement, the tropical Pacific was neutral, nothing to see. By the new one, a weak La Niña was already underway. September of 2024 is the month Hurricane Helene formed in the Gulf of Mexico, came ashore on Florida's Big Bend as a Category 4, and then did something almost nobody was braced for. Carried its moisture 500 miles inland, about 800 kilometers, and dropped it on the southern Appalachians, where the water came down the mountainsides and took out towns in western North Carolina that had never, in living memory, considered themselves at risk from a hurricane. I'm not going to tell you the index would have changed that outcome. It would not have. But it is worth sitting with the fact that the official state of the tropical Pacific, during one of the deadliest American hurricanes in half a century, is now recorded differently than it was at the time. And then there is 2023, which is where this whole reframing pays off. By the old index, that El Niño ranked as the 4th strongest since 1979, genuinely large. By the new one, it is substantially more modest, and the modest version is the one that matches what the atmosphere actually did, which was very little. Weak circulation response, a muted connection into North America, an Atlantic hurricane season that ran 40% above average when it was supposed to be suppressed. A study published last year filled in the mechanism. In 2023, the Indian Ocean and the tropical Atlantic were both running at record warmth at the same time as the Pacific. And when every ocean in the tropics is hot, the Pacific loses its monopoly on convection. The thunderstorms do not concentrate over the warm anomaly, because there is no longer a standout warm anomaly to concentrate over. The transmitter never switched on, because there was nothing left to transmit against. So the new index is a genuine improvement, and the people who built it deserve a great deal of credit. A senior scientist at the National Atmospheric Research Center in Colorado said publicly that it will give a more accurate picture of these events as the oceans keep warming. And I think that is right. But I want to be careful here, because there is a version of this story that ends with, "and then they fixed it." And that is not the story. There is also a practical wrinkle that is going to matter over the next 6 months, and I would rather you hear it from me than be confused by it later. Not everyone has switched, and not everyone switched to the same thresholds.
The American agency now issues its official probabilities on the relative index. Australia switched last September, but uses a different cutoff. Some research centers and the great many news outlets are still quoting the traditional number, because that is what their pipelines produce,
and because it is the number the public has learned to recognize. Which means that this autumn, you are going to see two different figures published for the same week, in the same ocean, by reputable institutions, and both of them will be correct. One will describe how warm the Central Pacific is. The other will describe how warm it is compared with the rest of the tropics. For a strong event, those two numbers can diverge substantially, and the second one is the better guide to whether your winter is going to feel like anything. So when you read a headline in October that says the index hit some dramatic value, the useful question is not how big. It is, measured against what? Now, back to the limitation, because it is the important one. The new index does not improve predictability. What it gives you is a better description of what is happening now. It says nothing whatsoever about what happens next. It resolves a labeling problem, not a forecasting problem. It explains the strange, muted El Niño of 2023 beautifully. What it does not explain is what came immediately afterward, when nearly every operational model on Earth called for a La Niña that arrived late, arrived weak, and in the year it mattered most, barely arrived at all. And a hurricane forecast worth billions of dollars had already been built directly on top of it. The timeline is short, and I want you to watch how fast the confidence drains out of it. Spring of 2024. The big El Niño has peaked and is decaying, and the subsurface Pacific is cooling exactly the way the theory says it should after a large warm event. The heat has been spent. The basin is in deficit. This, finally, is the textbook setup. The one that was missing in 2020. The models see it, and they agree. La Niña is coming, probably by summer. June. The models push the arrival back to early autumn and trim the expected strength. August. NOAA's outlook puts the odds of La Niña forming by the autumn at roughly 7 in 10. Still confident. Still coming. November. The same odds have fallen to a little under 6 in 10, and a good number of models have quietly given up and gone to neutral. What actually happened was that the event showed up months late, at the very edge of the definition, and was so weak that a full year later researchers were publishing papers about why it had failed to develop properly. One of them, out at the end of last year, said the quiet part in the abstract. It was unexpected that so many operational climate models significantly overestimated the likelihood of La Niña conditions in 2024. The subsurface cooling had been there, exactly as advertised. What never showed up were the easterly wind bursts that were supposed to convert that cooling into a coupled event. The fuel was in the tank. Nobody turned the key. Now watch what that did downstream. Because this is where an abstract forecasting problem turns into 250 coffins. On the 23rd of May, 2024, NOAA issued its Atlantic Hurricane Outlook. 17 to 25 named storms, 8 to 13 hurricanes, 4 to 7 major hurricanes, an 85% chance of an above-normal season. It was the highest May outlook the agency had ever issued in its history, and it rested on exactly two pillars. Pillar 1. The tropical Atlantic was at near-record warmth, which was unambiguously true and stayed true all season. Pillar 2. A developing La Niña, which would drop the wind shear over the Atlantic and let storms grow undisturbed. The Colorado State forecaster, whose team has been doing this longer than anyone, described it afterward as about as close to a sure thing as a seasonal forecast ever gets. Every major outlook agreed. There was no dissent worth reporting. Then came late August. From the 21st of August through the 2nd of September, straight through the climatological ramp toward the peak of the season, the 2 weeks when the Atlantic is supposed to be at its most productive, not a single named storm formed. That had not happened in 27 years. Labor Day weekend passed without a tropical scare anywhere from Texas to Maine. Reporters started writing the "What Happened to Hurricane Season" pieces. The Climate Prediction Center's chief long-range forecaster, asked to explain it, said plainly that it was an open question. The eventual post-mortems pointed to a pileup of small things. The African easterly waves that seed storms were tracking too far north, over the Sahara instead of over water, and dragging dry air out with them. The upper atmosphere over the Atlantic was anomalously warm, which makes it harder for thunderstorms to tower. There was too much easterly shear in the eastern and central Atlantic, and the global pulse of tropical convection that circles the planet every month or two was sitting in an unhelpful phase. None of which was La Niña, because La Niña, at that point, still had not arrived. And then the Atlantic woke up. Helene came ashore on the 26th of September as a Category 4. Milton followed roughly 12 days later. Between them and the rest of the season, more than 250 people died. Hurricane Beryl, back in early July, had already become the earliest Category 5 hurricane ever recorded in the Atlantic Basin.
The final tally for 2024: 18 named storms, 11 hurricanes, 5 major hurricanes, which fell inside NOAA's forecast range. Sit with that for a moment. The forecast verified. The number was right. And the number told you almost nothing useful about the season you actually lived through. A season with a hole in the middle of it, and a catastrophe stacked at the end. There is a cost to that which does not show up in any skill score. Somewhere in late August of that year, in a coastal county in Florida or Louisiana or the Carolinas, an emergency manager who had spent the spring telling residents that this was going to be a historic season watched 2 weeks go by with an empty Atlantic. And so did the residents. And a certain number of them concluded, reasonably, that the people with the computers had cried wolf. 6 weeks later, the water was in their living rooms. I do not say that to blame anyone. The forecasters did their job honestly. The science was applied correctly, and the range they published contained the answer. But a seasonal outlook is not really a number. It is a piece of communication, and its whole purpose is to change what people do in June about something that might happen in September. When the shape of a season stops matching the shape of the forecast, even a forecast that technically verifies, what erodes is not accuracy, but the willingness to act on the next one. Then 2025 did it again, from the opposite direction. 13 named storms, 5 hurricanes, below the long-term average on both counts. If all you saw was the scoreboard, you would call it a quiet year. It was not a quiet year. 3 of those 13 storms reached Category 5, Erin, Humberto, and Melissa. Only one season in the entire record has ever produced as many, and that was 2005, which managed 4. 4 of the season's hurricanes underwent extreme rapid intensification, blowing up from disorganized to monstrous in a day or two. The accumulated energy of the season, which measures strength and duration rather than head count, finished above average. And in the middle of it, there was another dead stretch. 20 days without a storm, straight through the September peak. For the first time since 2015, no hurricane made landfall in the United States. And on the 28th of October, Hurricane Melissa came ashore in western Jamaica with sustained winds of 185 miles per hour, right around 300 kilometers per hour, and a central pressure among the lowest ever measured in the Atlantic. It was the strongest hurricane on record to strike Jamaica, and it tied the record for the strongest landfall by wind speed anywhere in the Atlantic Basin, matching storms from 1935 and 2019. In the 72 hours before landfall, it had gained 115 miles per hour of wind speed, about 185 kilometers per hour,
which is roughly the difference between a stiff breeze and a demolition crew. Damage in Jamaica exceeded $12 billion, the costliest disaster in the island's history. Dozens of people were killed there, and dozens more across Haiti, Cuba, and Hispaniola. Now, I want to be scrupulously fair here, because there is a version of this that unfairly indicts everyone with a forecast desk. The short-range forecasts for Melissa were extraordinary. 4 days before landfall, the National Hurricane Center's projected track was off by about 13 miles, roughly 21 kilometers. 13. And its intensity forecasts beat every computer model at nearly every lead time, giving Jamaica almost 3 days of warning that a Category 5 was coming. That is as good as this science has ever been, and it saved a great many lives.
So the picture is stranger and more specific than forecasting simply failing. The 5-day forecast has never been better. The 5-month forecast is where the ground has moved. Look at what those two seasons have in common. In 2024, the count was right and the season was wrong. In 2025, the count was low and the season was violent. In both years, the seasonal number, the single figure that leads every news segment, that insurers price against, that emergency managers brief their governors on, described the year about as well as an average monthly temperature describes a week of weather. A forecast that says you will get 12 rainy days this year is accurate and useless if 11 of them arrive in the same week. By the end of 2025, that was the quiet consensus inside the field. Seasonal totals had stopped being a good description of a season. What nobody could agree on was whether that was bad luck, a run of unusual years, or the leading edge of something structural.
And then February came, and a small group of physicists in Germany published a single number, 91.4%, and turned an uncomfortable internal argument into a public examination. One that is being graded in real time, right now. So let me tell you what those physicists actually built, because the method is strange, and it is not remotely what you would expect. They do not model the ocean. They do not simulate the atmosphere. They do not solve a single equation of fluid motion. Instead, they treat the Pacific as a social network. So picture the setup. Take 14 points scattered across the central and eastern equatorial Pacific, the region where an El Niño eventually shows itself. Then take 193 more points spread across the rest of the tropical Pacific, well outside that box, 207 locations. Each one just a spot on a map where you can look up the daily surface air temperature going back decades. Now, for every possible pairing between the inside points and the outside points, ask a question. How tightly does the temperature at this one track the temperature at that one? Not whether they are both warm, whether they move together, whether when one twitches, the other twitches a few days later. Each pairing gets a number. Average all of them, and you get a single value that rises and falls over the years. They call it the mean link strength, and what it measures is not heat. It measures agreement. Picture a crowded room full of separate conversations. Ordinarily, it is noise, 200 people talking about 200 different things, nothing coordinated, nobody listening to anybody else. Then, without anyone announcing it, the conversations start to sync. People fall into the same rhythm. The room begins to breathe together.
Nothing has happened yet, but something is about to. That is what the tropical Pacific does in the calendar year before an El Niño. Long before the sea surface has anything to say, the far-flung corners of the basin begin agreeing with each other. And when that agreement crosses a specific threshold, a threshold these researchers fixed decades ago using data from 1950 to 1980 and have not touched since, they issue an alarm for the following year. I want to be precise about the track record,
because this is the part that makes the story bite. Between 2012 and 2025, this method made 14 forecasts in real time. Not hindcasts, not retrospective fits. Public predictions, time-stamped, made before the fact. 13 were correct. The single miss was a false alarm in September of 2019. The odds of a run like that coming from luck are somewhere around 3 in 1,000.
And their most recent triumph was the event we have been circling this whole time. In December of 2022, working from data that ended before the spring barrier had even begun, they forecast an El Niño for 2023 with a combined confidence near 90%. They forecast its magnitude at about 1.5 degrees Celsius, close to 3 degrees Fahrenheit, give or take. It came in at 2 degrees Celsius, near 3.5 Fahrenheit. They also forecast, months ahead, that it would be an Eastern Pacific type event rather than a Central Pacific one. All correct. So when this group published its outlook for 2026 in February of this year, people paid attention. And what it said was that the mean link strength had risen through 2025 from the very low values of the year before, but had never crossed the threshold. The room got louder. It never synced. No El Niño in 2026. 91.4%. Now, they were scrupulously honest about a complication, and I think that honesty is worth more than the forecast itself. They run a second, completely different method, one that measures not agreement, but disorder. A kind of entropy score for how chaotic the temperature record inside the Niño region has become. That method has its own decent hindcast record, and in February, it said the opposite. 71% chance an El Niño does start, though a weak one, peaking somewhere around 0.8 of a degree Celsius, roughly 1.5 degrees Fahrenheit. Two methods from the same group pointed at the same ocean, returning opposite answers. They handled the conflict by going back through 4 decades and finding every previous year where the two disagreed in exactly this way. There were 6. In 2 of them, an El Niño started. In 4, it did not. So they combined the answer, honestly. Roughly 37% odds of an El Niño beginning in 2026. Around 44% for a neutral year.
18% for another La Niña. For comparison, NOAA's official probabilistic outlook at the same moment was sitting at 61% for El Niño. There is one more wrinkle, and it is the one that keeps me up at night a little. The network method was originally built on one particular reanalysis dataset, one of the 2 great reconstructions of past global weather assembled in the United States. When these same researchers ran their identical method on the European reconstruction instead, using the same physics, the same equations, the same thresholds, the signal behaved differently. On the European data, the link strength did cross the lowest threshold, a partial alarm. Interpreted generously, that version would have implied roughly an 80% chance an El Niño was coming.
The same method, applied to the same planet, running on 2 different archives of what the atmosphere did, both assembled by serious institutions from the same underlying observations. And they disagree about the future, because they disagree slightly about the past. Then the year happened. April, neutral, and warming faster than most of the guidance had penciled in. The 11th of June, the Climate Prediction Center raises an El Niño advisory, conditions present, not forecast. The 9th of July, El Niño strengthening, 97% odds it persists into early spring of 2027, and an 81% chance of a very strong event during October through December that would rank among the largest in the record going back to 1950. Warm anomalies above 1 degree Celsius, near 2 degrees Fahrenheit, spread across the central and eastern basin, a downwelling wave deepening the thermocline in the east. Westerly wind anomalies at low levels across most of the Pacific. And this month,
An analysis of 667 separate model runs found that 91% of them project a peak later this year higher than the strongest El Niño ever measured. So the scoreboard for 2026 reads like this. The statistical method with the strongest public track record called for no event and got an event. The physics-based models, the ones carrying every bias I spent the last stretch of this story describing, called it correctly and early. And I want to be very careful with that, because it would be easy and wrong to walk away thinking the models are junk. They are not. This year, they earned their keep. If you are a water manager in Texas or a wheat trader in Chicago, the dynamical guidance gave you months of usable warning, and it is the reason anyone knew to prepare at all. The lesson is not that one tool beats another. The lesson is that no tool is reliably reliable anymore. In 2014, the models over-forecast an event that never came. In 2024, they over-forecast a La Niña that barely came. In 2026, the statistical challenger under-forecast an event that is now roaring. The errors are not converging, they are scattering. There is one more detail buried in that February paper, in the technical discussion where almost nobody reads, and I think it is the most consequential sentence anyone in this field has published in years. The researchers note that when their network method is applied to observations, it has real predictive skill. The record speaks for itself. But when the identical method is applied inside the major climate models, to their historical simulations and their long control runs, the skill is absent, or so low it cannot be used for anything. The precursor simply is not there. A companion paper published this year looked specifically at whether the current generation of models can generate this early warning signal at all, and found that they largely cannot. Stop and turn that over, because it is the quiet bombshell of this whole field. The signal that warns of an El Niño a year ahead exists in the real ocean. It does not exist inside the simulations we use to predict the real ocean. The models are not merely imprecise. On this particular feature, they are a different animal. A system that produces something that looks like ENSO, oscillates like ENSO, and can be scored against ENSO, but that does not contain the mechanism by which the real Pacific tips its hand. The authors suggest this may be exactly why models struggle so badly with the spring barrier, and that it may trace back to how they handle the coupling between air and sea. Think of a flight simulator that reproduces an aircraft perfectly. The handling, the instruments, the way it rolls in turbulence. Except that in the real airplane, 90 seconds before an engine fails, a particular vibration comes up through the floor, and in the simulator, it never does. You could train in that box for 1,000 hours and never learn the one thing that would save you. Which raises a question the field asks each other privately and almost never on the record. If the pattern itself is shifting under us, and the models cannot see the tell, then we had better be watching the real ocean more closely than ever. For the last dozen years, we have been doing the opposite, and the reason it started is almost absurdly small. It began with a ship. That array does not maintain itself, and the reason that matters is about to become obvious. That line of roughly 70 moorings across the equatorial Pacific was maintained, for years, largely by a dedicated NOAA research vessel that did nothing else. It sailed a circuit, pulling worn moorings, dropping fresh ones, replacing sensors that salt and sun and barnacles had killed. Unglamorous work. Thousands of miles from anywhere, for weeks at a time, in the flattest and most monotonous ocean on Earth. That ship was phased out, and between 2012 and 2014, the data coming back from the array fell off a cliff. Normal return had been 80 to 90%, meaning that on any given day, the great majority of those instruments reported. it dropped to around 40%. At its worst, it hit a record low of 30. Think about what that actually means. In the middle of the single most important decade for climate observation in history, the eye we built after the humiliation of 1982 lost roughly 2/3 of its vision. People in the field call it the Tau crisis, and if you have never heard of it, that is precisely the point.
Because an observing network does not fail the way a bridge fails.
There is no collapse, no photograph, no hearing. Think of the difference between a window breaking and a window fogging. Nobody has to explain a foggy window. You just start seeing less, and you adjust, and after a while you forget what the view used to look like. It got worse from a second direction. Japan's Marine Science Agency, which had built and maintained the western half of the array, began a phased withdrawal. Today, only a small number of near-equatorial moorings remain in the far western Pacific. And that western sector happens to be where the westerly wind bursts happen. It is where an El Niño is triggered, the exact stretch of water where the key that turns the engine gets turned. Did any of this actually degrade our forecasts? That is a fair and testable question, and it has been tested.
A study published a few years ago ran the 2015 El Niño twice through a forecasting system, once with the mooring data included, once with it withheld. With the moorings, the reconstruction of the ocean's temperature and salinity improved substantially in exactly the region that governs these events. And the 9-month forecasts launched from that better starting point were closer to reality in both amplitude and accuracy. The buoys were doing real work. Taking them out made the forecasts worse. That is not a matter of opinion. And it is worth putting the scale of the thing next to the scale of what it protects, because the two numbers do not belong in the same universe. A moored buoy in the deep equatorial Pacific, the anchor, the line, the instruments, the shipboard days required to place it and recover it, is an expensive object by the standards of an ordinary budget. Against the standards of a hurricane, it is a rounding error. Milton alone ran into the tens of billions of dollars. The Southern African drought of 2024 cost 6 countries their harvest, their grid, and a chunk of their national accounts. The economic losses attributed to the two great El Niño events of the 1980s and 90s run into the trillions. You could maintain that entire line of instruments across the widest ocean on Earth in perpetuity for what a single mid-sized landfall costs the American insurance industry in an afternoon. I am not making a policy argument. I am making an arithmetic one. Observation is the cheapest thing in this entire story, and it is always, always the first thing that goes quiet. Because a buoy that keeps reporting produces no headline, and a forecast that was correct because the data was good produces no headline either. Prevention is invisible by design, which is the whole problem with funding it. Now, the standard reply is that we have better tools these days. And there is something to that.
Argo floats drift through the world's oceans, diving and surfacing and profiling the water column. Thousands of them. Satellites measure sea surface height precisely enough to see the bulge of a passing subsurface wave. But there is a reason a weather station is bolted to the ground instead of carried around. A drifting float gives you a snapshot of wherever it happens to be. A mooring gives you the same spot, over and over, for years, which is the only way to see a change rather than a difference. And satellites read only the skin of the ocean, the top fraction of a millimeter, while the story that matters is happening 100 meters down, around 300 feet, in water no photon has ever touched. Nothing in orbit measures the wind at the sea surface on the equator continuously and in real time. The moorings do.
The central and eastern portions of the array recovered after 2015,
and an international project was launched to redesign the whole system for the modern era. That work is real and ongoing, and the funding argument has not gone away. The federal budget request for this fiscal year proposed eliminating NOAA's Research Line Office and terminating its climate and ocean laboratories and cooperative institutes. In the appropriations law that Congress ultimately passed, the office was retained, with its funding reduced by roughly 10% and a subset of programs transferred to the National Weather Service. The same debate is already underway for next year. That is the factual state of play. It will be settled by Congress and not by me, and reasonable people hold different views about the right level. What is not in dispute is the physics. Every instrument in that water is a line of defense against being surprised. And the agency is investing on other fronts at the same time.
This hurricane season, for the first time, data from small uncrewed aircraft is being fed directly into the operational hurricane model, alongside new artificial intelligence-based weather systems and next-generation satellites. So we are simultaneously sharpening some senses and letting others blur, which would be a manageable trade if the thing we were watching had agreed to hold still. It has not. And that brings us to the argument currently splitting this field down the middle, an argument that is not at all the one you would expect. You would expect the debate to be about how much worse things are getting. It is not. The two camps disagree about the direction. Camp 1 says predictability is falling and has evidence. A study in Nature Communications a couple of years ago separated these events into their two known flavors. There is the classic Eastern Pacific type, where the warmth concentrates off South America. That is what 1997 was, and it is what this year's event appears to be. And there is a Central Pacific type, where the warmth sits out near the dateline and the Eastern Pacific stays comparatively cool. They share a name on the map, and almost nothing else about where they live. And the two of them can produce opposite outcomes in the same country, in the same winter. That study found that under greenhouse warming, the Central Pacific flavor becomes measurably harder to predict. The spring barrier for that type is projected to strengthen by about a quarter. The mechanism is that a warmer surface loses heat to the atmosphere faster, which damps the growth of anomalies, which means events emerge later from a smaller, noisier signal. The Eastern Pacific flavor, meanwhile, is expected to stay about as predictable as it is now. Now the sting. Other work suggests the Central Pacific flavor, which is the harder one, may become the more common one.
So we would be shifting toward the type we are worst at. There is supporting evidence in the operational record too. An evaluation of multi-model hindcasts found that skill for the Standard Pacific Index was substantially lower over 2000 to 2018 than it had been from 1982 to 1999, with the sharpest losses precisely in the late spring and summer targets at longer leads. And part of the reason appears to be that the statistical relationship between the extratropical North Pacific and the tropics weakened after 2000. One of the reliable predictors simply got quieter. Now, Camp 2. Earlier this year, in Science Advances, a team including that same Seattle oceanographer published the opposite result. Using a deep learning approach across large model ensembles, they found that ENSO predictability has been enhanced by about 14% under historical human-caused forcing, plus or minus a couple of percent. Their mechanism is physical and specific. As the planet warms, the thermocline in the equatorial Pacific shoals. It rides closer to the surface. A shallower boundary means the surface responds more sharply to wind, and the subsurface responds more sharply to changes in the boundary's depth. The feedbacks get stronger. Stronger feedbacks mean a bigger signal relative to the noise, which means more predictability, not less. And there is a third position that reconciles a good deal of this. A paper in the Journal of Climate last year found that predictability tracks amplitude almost mechanically. Change the size of the swings by 10%, and you change globally averaged forecast skill at a 1-year lead by about 14%. On that view, the question, is ENSO becoming more predictable, collapses into, is ENSO becoming bigger or smaller? And that too is unsettled. So, less predictable, more predictable, or it depends.
3 careful groups, 3 defensible answers, all published within about 2 years of each other. I find that clarifying rather than discouraging, and here is why. Every one of those results is about the theoretical ceiling, how much predictability exists in principle. None of them describes what the operational forecasts actually achieved in the real world, which we already saw earlier. Beyond 3 seasons of lead time, real-time calls on the onset of an event landed correctly less than 1 time in 5. The ceiling argument and the floor argument are different arguments, and we are nowhere near the ceiling. Which is where the machines come in, and this is where the story finally starts pointing upward. A team in South Korea and China published something in Nature back in 2019 that reset expectations. They trained a neural network of the kind used for image recognition to look at maps of ocean temperature and heat content and predict the Pacific Index months ahead. Because the observational record is short, only a few strong events since satellites existed, they trained it first on enormous archives of simulated climate, then fine-tuned it on the real world. That network produced useful skill out to about 1.5 years, beating the physics-based models at every lead time beyond 6 months. The field took off after that. Transformer architectures reaching 18 months and beyond, networks trained purely on observations reaching 20, hybrid systems that let a physics model and a neural network correct each other, published last year, outperforming either alone. And a technique based on information theory, published this year, claiming skillful forecasts of the phase out to 2 years. If any of that holds up in real time, and real time is the only test that counts, it would be the largest advance in seasonal forecasting since the boys went in. But you already know the catch, because I have been building toward it for the last hour. Most of these systems were trained on output from the same generation of climate models that cannot reproduce the observed Pacific trend, and that do not contain the early warning signal the real ocean produces. A network trained on that archive has learned the simulated ocean with tremendous fidelity. A student who memorizes a textbook with a typo on page 48 will answer faster than anyone in the room, and will be wrong about page 48 every single time with total confidence. The researchers know this. The best current work explicitly attacks it, training on observations directly, building interpretability tools that show which regions the network is actually keying on, and finding, reassuringly, that the machines are leaning on the tropical Pacific with contributions from the Indian and Atlantic, which is exactly what the physics says they should. That is a field policing itself properly, and it deserves to be said out loud. Still, whichever camp turns out to be right, the argument is not being settled in a journal. It is being settled in October, in a field outside Chipata in eastern Zambia, when a farmer decides which seed to put in the ground. Because the last time the models were confident about southern Africa, 6 countries declared a national disaster. That was the season of 2023 into 2024, on the back of the muted El Niño we have already discussed, the weak one, the one the new index would later downgrade. Weak out over the Pacific, and nothing like weak by the time it reached the ground in Africa. From January of 2024, huge areas of Zambia, Zimbabwe, Malawi, Angola, Mozambique, and Botswana received less than 1/5 of their normal rainfall. February was the driest in decades. The rains failed at the exact point in the growing cycle when maize sets its grain, which is the moment in the calendar when a crop is either made or lost. In Malawi,
The president declared a state of disaster in 23 of the country's 28 districts. Close to 44% of the national maize area was hit. In Zambia, 84 of 116 districts. Across 10 countries of the Southern African bloc, the maize harvest came in around 28 million tons, about 9% below the 5-year average, which sounds survivable until you look at where the shortfall concentrated. Maize prices in South Africa ran nearly 50% above the previous year. In Zambia, above 55. And the drought took the electricity too. The Kariba Reservoir, which Zambia and Zimbabwe share and depend on for hydropower, fell so low it could barely turn a turbine. Both countries went into rolling blackouts lasting hours and sometimes days. In Zambia's case, in a year when its people also could not afford food. Namibia and Zimbabwe authorized culling wildlife, including elephants, to distribute meat. The World Food Programme put the number of malnourished children across southern Africa at around 21 million. 6 countries in that region declared a national disaster or emergency that year: Botswana, Lesotho, Malawi, Namibia, Zambia, and Zimbabwe. All of it out of a single growing season. From an El Niño that the atmosphere over the Pacific barely acknowledged. And on the other side of the world, the same event was writing a different kind of casualty list. In March of 2023, a tropical cyclone called Yaku struck the normally bone-dry northwestern coast of Peru at the same time as a localized coastal warming event. Flooding, mudslides, roads and bridges gone, and in the standing water that stayed behind, mosquitoes. What followed was the largest dengue outbreak in Peru's recorded history, incidents running 10 times the 5-year average, and 381 deaths in 6 months. A study published this year, led out of Stanford with Peru's health ministry, estimated that roughly 60% of the cases in the hardest-hit districts were directly attributable to the extreme rainfall and heat. Globally, 2023 set a record with 6.5 million dengue cases and more than 6,800 deaths. Then, 2024 doubled it. I know that is a great deal of suffering delivered quickly, so let me tell you why I put it there. Every one of those numbers is downstream of a forecast. Somebody, months earlier, was told what kind of season to expect. That information determined which seed varieties were subsidized, whether grain reserves were released early or late, whether mosquito control was funded before the flood or after it, how much cash an aid agency asked donors for in the appeal that gets written a full year ahead of the crisis. Those 2 researchers at Dartmouth who followed the money forward on past events also ran the arithmetic on the future. Under an emissions path consistent with current pledges, their projection for the economic cost of intensifying ENSO variability across this century came to $84 trillion. Which is why I would ask you to think of the forecast as infrastructure rather than as a curiosity. So, where does that leave us right now, in this specific July? Here is the honest picture, and I am going to give you the alert levels and the caveats along with the drama, because you deserve both. An El Niño advisory is in force from the United States Climate Prediction Center. In operational language, an advisory means conditions are present rather than expected. The World Meteorological Organization's global producing centers are in agreement. Australia's Bureau of Meteorology is tracking the same warming while reminding everyone, correctly, that a strong Central Pacific signal does not guarantee strong local impacts anywhere in particular. Humanitarian agencies preparing for the next 12 months have issued internal guidance recommending that the phrase Super El Niño be avoided in operational communication, not because the event is small, but because the phrase promises a certainty that does not exist. I would ask you to hold that standard for anything you read about this over the coming months. What we know. The ocean is warming fast. The Eastern Pacific is running far hotter than the Central Pacific, which points toward the classic eastern type.
The atmosphere is coupled this time.
The pressure seesaw between Darwin and Tahiti has been running deeply negative since June, which is the response that failed to materialize in 2023. What we do not know, the peak, the timing, and above all, whether the rainfall response follows the water. That is the fracture that broke the last event, and it is the single thing I would watch above all others. So here, concretely, is what the people whose job this is will be staring at between now and Christmas, and you can watch the same things they do. First, the relative index, the new yardstick, not the old one. Whether it keeps climbing through the autumn, and how far it diverges from the traditional number. The gap between those two figures is, in effect, a live readout of how much of this event is really the Pacific, and how much is simply a warmer world. Second, the cloudiness near the dateline. It sounds like a footnote. It is the whole broadcast. Forecasters track the amount of infrared radiation escaping to space over that stretch of ocean, because when deep thunderstorms are firing there, less heat gets out. If that signal stays strong through October, the teleconnection into North America is live. If it wobbles, we are heading for 2023 again. Third, the subsurface. Whether the reservoir of warm water feeding this event is still being replenished from the west, or whether we are already watching it drain, which is what tells you when the peak arrives and how sharply it falls away afterward. Fourth, the Indian Ocean. If a positive pattern develops there as expected, it moderates the Indian monsoon and floods the Horn of Africa. If it does not, both of those forecasts move. And fifth, the trade winds themselves. Sustained westerly anomalies mean the engine is still being fed. A sharp easterly surge, the same thing that killed 2014 in a matter of weeks, would change this entire conversation before Halloween. Those 5 things, rather than the headline number that will be sitting on top of them. For East Africa, the current expectation is genuinely hopeful. An El Niño combined with a developing positive Indian Ocean pattern should push October through December rainfall above average across southern and southeastern Ethiopia, northern Kenya, and southern Somalia, after a season last winter that was among the driest on record and left between 20 and 25 million people needing food assistance. That would be recovery. It would also, on ground baked hard, bring flooding. Both things are true at once. For southern Africa, the risk is not this year. It is the growing season of 2026 into 2027, which begins in a few months.
For India, the meteorological department moderated its monsoon outlook from deficient to below normal, precisely because a positive Indian Ocean pattern is expected to partially offset the Pacific. That is a forecast built on 2 oceans arguing with each other, which is exactly the world we now live in. For the United States, a wetter, cooler southern tier this winter, a milder north, real potential for drought relief after 6 dry years, elevated fire risk in the Pacific Northwest come spring, and California as the wild card it always is, and an Atlantic hurricane season that everyone expects to stay quiet, from forecasters who have been burned before. Now let me pull the camera all the way back, because there is one last thing to see. For most of the 20th century, we treated this as a Pacific problem, a closed loop between one ocean and the sky above it, with a rhythm, a trigger, and a memory. That model was beautiful and largely correct, and it earned humanity the single greatest gift climate science has ever handed us: months of warning. Everything in the last 15 years has been the system telling us that the loop was never closed. The Indian Ocean has a hand on it. The Atlantic has a hand on it. The subtropical South Pacific has a hand on it. Cloud decks off Chile have a hand on it. And underneath all of them,
The background state the whole thing operates against has been quietly moving for 4 decades in a direction our best simulations did not anticipate and still cannot reproduce. Go back to Walker's seesaw one final time. He found a rhythm in a stack of barometer readings and could not say what caused it.
A century later, we know exactly what causes it. We can watch it from orbit. We can measure it from inside the water. We can simulate it on machines that perform more calculations in a second than he performed in his life. And we still cannot reliably tell you what it will do next summer. Because he was measuring a seesaw on level ground. We are measuring one on ground that is rising. This is not a story about broken models. It is a story about a broken assumption. The assumption, buried so deep in the discipline that almost nobody stated it out loud, that the climate would hold still long enough to be learned. Every forecast ever made is a promise about a world that has agreed to stay the same shape. And here is the part I would like you to carry out of this. None of that is an argument for despair, and it is certainly not an argument for ignoring the forecast. The short-range hurricane track is the best it has ever been, and it saved lives in Jamaica in October. The famine early warning networks called East Africa's failed seasons months ahead and moved food.
The dynamical models called this El Niño, while the challengers said no. The tools work. They are simply working on a moving target now, and everyone using them has to hold them a little more loosely than we did in 1997. So we go back to what 1982 taught us. The answer then was not to argue. The answer was to build a better eye. There is a line of buoys out there tonight, fewer than there were 15 years ago, strung along the equator in water miles deep, rising and falling on a swell that has been rolling west since long before anyone was here to name it. Every few hours, each one reaches up to a satellite and hands over a number. Tonight, those numbers are the warmest anyone has ever recorded in that place. The trade winds have already slackened. The thunderstorms have already started walking east.
And somewhere between October and January, we are going to find out whether this ocean is repeating a sentence we know by heart, or beginning one nobody has ever heard. We will know more in the coming weeks, and we will be watching exactly the same signals the forecasters are.